As Berton mentioned last week, he's not in town today, so I'll come here for the lecture 11. Today we'll go the same topic from LandNet to ResNet and Power 3. It's still a brief history of CNNs. Okay. Actually, because I'm PM, so I have to talk at least one lecture. And I'm very happy to have this one because this lecture 11, gives the introduction to ResNet, which is very important, obviously the most important network or publication in computer vision or even in deep learning. This paper published in 2015. And then you can see it's the first time the performance of a network or a manually designed model to outperform human performance in ImageNet. I guess since we have talked about ImageNet for like 2 or 3 lectures, I guess you may have already taken a look at the ImageNet. It's a very big data set, and there's a lot of very challenging images. And since that time, since 2015, we start to outperform human beings. And also this paper, ResNet, published by Taiming, is I guess it's best paper in CPR 2015 or 16, I'm not pretty sure, and it's the most cited paper in computer vision. Oh, sorry, in deep learning. So it's a very important structure. Actually, you do not have to use ResNet because it's a network. You only need to use, they developed a block called REST block, and for this block, they give a network called ResNet. But you only need to use the REST block, as I will mention it later. And different from the like AlexNet or VGG, and maybe GoogleNet. No one uses it anymore, but we still use ResNet. And if you read some papers in computer vision, even nowadays, we still compare to the performance. We still compare to the ResNet, and sometimes we still use the ResNet as a backbone of our network, and we maybe some guys develop some new loss function or something and do some adjustment on ResNet and they get their paper published. But basically it's ResNet. Well, here is the length of the ResNet. As you can see, the tiny AlexNet and tiny VGG19. And usually we use VGG16, not 19 actually. We will talk about why we use. We do not use VGG and we do not use VGG19 now. And here's the ResNet. It has 150 layers. And actually, Kami used this structure for the ImageNet Challenge 2015. Actually, they published a ResNet with depth over 1,000 layers. Much bigger. Yeah, here's their paper, best paper in CPR 2016. Actually, if you know the like deep learning history or something in 2015, 2016, you will notice that at that time, actually, the deeper network get the better performance. So I remember it's like 2016 and 2017, everyone is going to make their network bigger and bigger. So if I can train a network with like 50 layers before ResNet, sorry. If I can train a network and make it work with 30 layers, I get a performance. And some guys get a network like deeper, like 50 or 60 layers, and it also works. It definitely works better than my model. That's the condition at that time. But there's a challenge. Actually, look here. But if we use like VGG type, we call it the planned convolution neural network. What do you think if we make the network deeper and deeper? You may have some problem. That's why, yeah.
Does it take longer to train?
No, because you can see it when you publish. In most publications, we do not care about time. We just care about the accuracy in most conditions. Sorry. Any? Yeah.
Would you have less gradient at the top of the?
Yes. Yes. When your network get deeper and deeper, the gradient will get tiny and tiny, and finally your network will almost impossible to train. You can see from here. By comparing the 20 layers and 56 layers, here's the iteration, means how many times you train the network, and this is training loss and test loss. As you mentioned, in either training or test, we got a bigger loss in the deeper network. Right? But why? As you mentioned, it causes overfitting. Here's what mentioned by Kami. He gave a hypothesis that the problem is an optimized problem. Deeper models are hard to optimize. If you do not, how to say, yeah. a deeper model should be able to perform at least, it should be perform at least as well as a shallow model, because the deeper model compares more parameters, right? If you can train this deeper model, of course it should perform at least as well as the shallow models, because it has more parameters and it can it can use for more complex things, right? Complex transforms or anything like that. So can we propose a solution by copying the learned layer? Sorry, it's not proposed by Kami. It's a old-fashioned method. It's like, for example, if we have a VGG16 and it's well trained, right? It's working now, VGG16. But now I want to have a more deeper network. What should I do? A very easy idea is that I have two VGG16 and get them together, connect it. Both of them are well trained, so they should work in some level, right? And I train this contacted model with like 32 layers. So it's, obviously it doesn't work. If it works for, we call it pre-train or something. Maybe you can call it pre-train, or it works if you have only like 40 or 30 layers. You can use some pre-train model and contact it together, and then after contact the pre-train model, you train it with your data set. And sometimes it works, but it not always works. Here's the primary solution. He used a network layer to fit a residue map instead of directly trying to fit a underlying mapping. It's like we usually get an input X. It's called plan layers. We call it plan layers. Anyway, we got input X, and we do some convolution or ReLU or bunch normalization. Anyway, we got output HX, right? But once you do backpropagation, you need to calculate the loss here. You need to, when you do the backpropagation, here's the loss, and the loss also needs to come through all of these convolutional layers. And it gets smaller and smaller, right? Here's our chemistry solution. Actually, it's a very obvious idea, but no one knows at the time. It's just, I have an input, and of course I need these convolutional layers or ReLU or batch normalization. But I have a bypass to pass this value directly to the output. So I have fx come from this convolution and plus this x. Well, this bypass, when you do the backpropagation, the loss can directly come here. The loss do not, of course, the loss comes through these convolution layers, but it also comes by this way. So when you have a deeper, much deeper network, it will help you to get a bigger loss. When you do the bigger loss, it's like to get a bigger value when you do the backpropagation, which makes you much more easier to train your network. Any question about this model? Actually, this one is a main contribution of the chemist work, and this one is called residue block. And actually, nowadays we replace the normal convolution with such residue block. You can replace any convolution layer with such block, and also you can change this. This is the original rest block. Anything with this bypass is called rest block. So you can put different convolutional layers here or different kernels. We will mention the kernel later. Yeah.
So you're just like re-injecting X some amount of layers down so that the gradient stays large as you go deeper and deeper.
We need to make progression. Yeah. It's like, yeah. Here's a rest net. It's called rest block, as we talked earlier. And this is a rest net for ImageNet. It have 152. Actually, here you get input, and you got a 7x7 convolutional layers to slide 2, actually, 4, to make it smaller. And then you can see the rest block with different. The kernel is 3x3, and channels get upper from 60 to 128. Actually, it's a, we call it, no, not encoded. But the channels first it get bigger from 60 to 128 to 56 and 512, yes. And then from 512 go down to 256, 128, and 16.4. And finally we get a pole and FC 1000 to get a, because ImageNet have 1000 classes. After FC we have a softmax to calculate the loss for training. Polling layers?
Yeah.
Yes, because it uses slide 2 to make the size smaller, to get half size, right? Slide 2 and maybe slide 2 here, as we mentioned in last lecture. Yeah, it still use FC layers, which we never use it today because it's so heavy. Yeah, the main contribution, as we mentioned, is use layers to fit residue fx equals hx minus x instead of hx directly. Yeah. Here's the full ResNet architecture. At this version, actually very early version, every residue block have two 3x3. We said 3x3 convolutional layers, 2 conv layers, and ReLU. This is their like alpha version ResNet block. And they put this residue block together, like this, only change the channels. It may be a little painful to read from this figure, but it will be much more easier if you read their source code of the network. It's very simple, and you can just Ctrl+C and Ctrl+V. Then the network appears. So they repeat the same things, makes you very easy to build a deeper network, since that time we still use Caffe instead of PyTorch or TensorFlow. So you need to write C++ code to get this cover. Yeah. As I mentioned, here's the kernel size, layer name, and the channel. They double the filter and downsample using slide 2, not polling layers. It should have the same performance if you use polling layers. not much different actually. Yeah, here's the additional layers, the beginning cover layers. Actually, for all ResNet-like or ResNet format, or maybe, yeah, they have a beginning cover layers and an ending cover layers, which is FC, and nowadays we turn it to like cover layers plus global average polling, but we have a beginning and an ending, and in the middle it's in the same form. Let me see. Yeah, if you can remember when we have VGG16, we have two FC layers, right? For example, if we use VGG16 for ImageNet, we should have a FC like FC 1024 and FC 1000 for different classes. But in this, from this block, we do not need that much FC layers. The ResNet only have one FC 100 layers, and we'll mention it later. You'll see that more modern networks do not need FC layers anymore. That's the difference from the VGG. Actually, we compare ResNet with VGGNet because GoogleNet is completely not the same type, right? They have different kernel size, like 3x3, 5x5, 7x7. Yeah. ResNet 15, or someone call it 52. You have a lot of options if you chose ResNet. We have some shallow network called ResNet 34 with only 34 layers. Of course, we have some deeper layers. It's like 50, 101, or 152. You can choose these models based on your, nowadays we have GPU, our GPU have memories bigger than like 24 gigabits. So we can have, of course we chose the 152 if we have to choose one, because they have a better performance. But at that time, like NVIDIA only have GPUs with like 8 GB memory, 8 GB memories or like 4 GB memories. So we have no choice. We have to use some shallow networks. Yeah. For deeper network, here's another format of the REST block. Can we publish a different type called bottleneck ResNet block for some deeper network to improve their efficiency. It's similar to Google Analytics. Yeah, because they use, if we simply use 3x3, two 3x3 cover layers, and the input shape and the output shape, of course it should be the same, but it will use more memory. That's what I mentioned. At that time, we have very limited memory size, GPU memory size, sorry. So if you want to use our deeper network, like 101, you have to try some different method to make your network to not that GPU hungry, to not take that much memory. So they also provide that bottleneck structure, which can dramatically reduce their memory usage. Actually, this cover layers is just turning this 28 by 28, 256 channel input. It's a input into a 28 by 28 by 64 channels. So both this one and this one is only trying to reshape the channels. And this one, we usually to have two converter layers, 3 by 3, and now we only use one. And separate another 3 by 3 convolution layers, the learning parameters into these two 1 by 1 converter layers, because they are not simply reshaped, right? They are converter layers. They still have learning parameters, so they still can learn something, but it will take much less memories. So that's why he proposed this structure. Yeah, this is experiment details for the training ResNet. Maybe I go too fast. They have batch normalization after each converter layers. Batch normalization is a very powerful weapon to training a deep learning model. We still use it nowadays. We do not use drop off anymore. Like we drop 50% of the parameters when training. No, we do not use it anymore. We use batch normalization. And this is what we are going to introduce later. Can we also produce initializing method? Because maybe some of you have started homework too, I guess. They have some part need you to build a network using PyTorch, right? And when you build a network, before you start training, you need to initialize the parameters. If your network is not that powerful, it's not very powerful actually, the initializing method will make very big difference for the final result. I mean, if you use like initialization method 1, you will get like accuracy 98%. And if you just change the initialization method to like method 2, you will get a prediction accuracy maybe only 90. So that's why, and the ResNet is for challenge, right? So we want the best of the best. So we change everything we can change. So they proposed the initializing method. And they use SGD plus momentum and always 9.9. SGD plus momentum is very popular at that time. But this training method, SGD method, is actually it's a pretty naive method and pretty rely on hyperparameters. You need to very carefully adjust the learning rate and momentum and like divided by 10 or by what when you should reduce the learning rate. So this method is heavily dependent on the hyperparameters, but we only have SGD plus momentum at that time. Now we have like Adam or something. You actually do not need to adjust anything. You just tell the network, okay, I have a network, and you use Adam to train it, and it will calculate which learning rate is the best for now, and when should I reduce or increase the learning rate. But it's 2015. Learning rate they use 0.1, and they divide it by 10, like 0.1 and 0.01, 0.001. One validation error plastics. Yeah, because you have training and validation, right? If your validation is stable from epoch to epoch, like from iteration 10 to iteration 15, your validation error is not decreased. We saw maybe your network is, maybe your learning rate is too big for this level. So we need to reduce the learning rate to make the network to learn some tiny things, to learn some tiny difference. And in this way, we can make the validation to go better. We have mini batch size 256. Actually, it's not very important. No, since ImageNet is though it's a very big data set, but their images is very tiny, so you can have 256 or even more. But if you use some bigger images, of course your GPU could not handle such size. Maybe you have 128 or maybe 64. Their weighted decrease, no dropout used because we have batch normalization. Weighted of, oh, this one is for their SGD. No. The learning rate is for SGD, and this one, I could tell with, let me check. I could. I'm sorry, but I didn't remember where this parameter works, but.
Isn't that for normalization?
For batch normalization.
But that's, I've seen you use the weight decay when he was talking about, because you times the weight decay by the weight square. Usually, that's what we've done so far.
It's called the learning rate. You mean the loss we
No, not the learning rate. This is for like, so you have your, because we did linear class, or just, you do the W times X plus B for a linear classifier, and afterwards, you add weight decay times the weights squared for the normalization part. But I didn't
yeah.
say
Yeah, it's for
Sorry, regularization.
Yeah, it's for the regularization. Yeah, sure.
But I didn't see any regularization like blocks in there. But is that part of the loss at the end? Is that part of softmax regularization?
No. We do not have regularization softmax. It should be for batch normalization, I guess. I'm not pretty sure, but I'll check it later. But what I am sure is that you will not need to change this parameter. It's fixed, and everyone uses the same value. Actually, if you use SGD plus momentum, no one changes momentum 0.9. We always use 0.9. Or you can use 0.99. But no one uses different values. Okay, then we'll introduce the initialization method proposed in the same paper. That's why it got a best paper in CPR, because it publishes a lot of things in one paper, and it's super amazing. So actually I'm not that familiar with this part actually, but this is here's a reasonable initialization. Mathematical derivation assumes linear activations. Yeah, layer standard is here, this part. So yeah, this W equals numpy random n. This one is a original, we call it original layer initialization method. It's a random initialization. I see, I remember now. I guess none of you have ever heard this initialization method because later we found it's not that good as it said. Yeah. Usually it should have distributions like this way. When you have ReLU, in ResNet we have ReLU after each convolutional layers, right? When you use ReLU, it do not distribute in the same way, right? The distribution is obviously not the same. And then after your initialization, you can see it's all very close to 0. So it should be from 0 in the middle. It should be positive and negative equally distribution, something like that. When you have ReLU, you pass through all the minus bar cutoff. And of course, this will it will make it more challenging to train the network if you do not have a good initialization. For example, if you initialize all of the width to 0, obviously it will never get trained, or it's almost impossible to get trained. So we want the initial weight to have a standard distribution. So here's what can be proposed. The only difference is this 2 by Fanny here, the score. You can see here's score Fanny and the U score 2 by Fanny. Why we say obvious? This is a figure from their paper. We always chose the best performance to show in our paper. Obviously, we chose the best of the best image in our paper. But you can see here, there's some difference, obviously, but not that much, right? Far from this one. So that's why this initialization method do not get as popular as the ResNet. But in their figure, they show that our proposed initialization method have a very good performance. Actually, we take it because it's published by Kemi. Actually, at that time, a lot of new, we have new, in 2015 or 2016, we have new network structures, we have new loss functions, new learning strategies, like SGD, new initialization method, publish, or even publish in top conference. But most of them is not that useful. So I'm not that surprised this initialization. This show worked very good, but actually not. And times will show that no one uses it anymore. So it's not good. Any questions about, let me finish the last one. The owners for the ResNet. Once ResNet come out, it immediately becomes the top one in almost every challenges. I should say common data set, like ImageNet and MS Coco. ResNet, some guys may try ResNet in some medical images or some like cells or like X-ray or something. It do not work that good. We have different network structure called UNet for that specific task, but for general tasks like human being, airplane, or cat, dog, ResNet immediately becomes the first. So, because ImageNet, is anyone check what ImageNet is, or what ImageNet contains? No. Okay, maybe it's too big. ImageNet contains, at least they have 3 actually. Classification for give you an image, dog or cat or airplane. Detection, an image, where's the dog, where's the cat. Localization, what's ImageNet localization? Match. Or now we have ImageNet segmentation, like detection is to give a bounding box where the dog is, and segmentation is like give which pixel belongs to the dog, which not. And they're 60% better than the second, maybe 27 better. MS Coco, actually MS Coco is bigger and is more challenged than ImageNet. Oh, yeah, here. MS Coco segmentation. ImageNet do not have segmentation tasks. Only MS Coco have segmentation tasks. But to be honest, the MS Coco is our data set is public, is proposed by MSRE, and Kami is a leader research scientist in MSRE, so you know that. Your own data set and your own method, you can test as many times as you wish, and once you get a good performance, you publish the data set. Obviously, you are the top one. The experimental results with the REST block, another ResNet. With the REST block, we are able to train very deep networks. Yeah, they have 1,022 on C button. Deep network now achieve lower training error as expected. Actually, this also means we can train a deep network, because if a deeper network did not provide a better performance, it means we are not well trained this network, which means we could not train a deep network. But now it have a better performance, so now we can see deeper network have more parameters. So once we can use all of these parameters, we should have a better performance. It becomes top in all ImageNet and MS Coco 2050 computations. Yeah, that's the most important part because it's the first time outperform human being. It's error chip. Do you have any idea what top 5 error means? Yep. No?
Isn't it? I think you explained it last time. It's just like you take the top 5 predictions.
Yes.
What's the correct prediction?
In the top 5, yes. So we can. It's too hard to take the top 1 error because we only take the top 1. It's even challenge for human beings. So you have, since there's 1,000 of classes, if you only take top 1, maybe the top 1, the prediction accuracy is like 25.01%, and the second one is 25%. So it's almost the same. So we usually compare the top 5 errors. Yeah, we have this figure again. And then you can say from 2015, from ResNet, we have a deeper layers and SCNet. We'll mention SCNet later. SCNet is another very good structure. Yeah. That's all about ResNet. Do you have any further questions about ResNet? We'll go some more new. Yeah. As you mentioned, the time, right? The training time. Actually, as you can see here, we do not compare the training time because these guys believe we have almost unlimited time to train a network. If the network can work fast when it do the prediction, we do not care how much time it takes to train the network. We can train elsewhere. We have someone else to train it for me. But I care about how much memory it takes, how much time it takes to predict. When I use this network, when I use a well-trained network, how much time it takes? Well, here's here's the comparison to the top 1 accuracy. ResNet here, as you can see, VGG, and ResNet 34, 50, 101, 152, and Inception V3 and V4 is like GoogleNet plus ResNet. But we still prefer to use GoogleNet if we want a faster network. We'll see here. Here's the accuracy, right? Operation. Here's the operations. Means how much time it takes when you do the prediction, when you use this network. And the size of the circle means how much memories it needs. Means it's the parameter size. So it have like 5 million parameters or 100 million parameters. It will make how many GPU memories you need. And here's VGG16 and VGG19. It takes a lot of memory and a lot of option, but not that good performance. That's why no one uses it. But no. The InceptionNet V4 is a ResNet plus Inception. So it's like, as I mentioned, you use residue block to replace the convolutional layers in GoogleNet. The VGG, both VG19 and 16, highest memory, most operations, which means it's time costing, and memory heavy, and worse accuracy. Here's a GoogleNet. It's the most efficient one because it's have a very tiny parameters and very less operations. Actually, we use GoogleNet. We still use GoogleNet when we do some applications. Like, I believe some of you use Windows Hello to log in. We use GoogleNet we used to use GoogleNet actually at that time in Windows Hello too, because we needed to process fast. When we can accept this accuracy reduce, because we do not need to be 100% sure, maybe 90% sure, or 80% sure is good enough, but we want it faster, even in your cell phone, in everything, like PC, cell phone, and some gaming machine. We want it faster because the customers is more sensitive to the time, because not the accuracy. So once you use your iPhone Face ID to log in, sometimes it's oh, the post is not good. Try it in different angles or in different ways or something. But just imagine if your Face ID takes 3 minutes to decide whether you are the right person to unlock the phone, or you will drop it immediately. So when we do a product, we want it to be faster with an acceptable accuracy. The faster the better. That's why GoogleNet is still we're still using it in all these things. And ResNet obviously have almost the best performance. If you a little better than 1.1. If you are trying to publish some paper, right? You are doing some research. You only care about what the reviewer cares. So the reviewer can only get, if you do not mention your parameter and prediction time, they will never know. You just publish look, I have a very good accuracy, and look at my prediction, well, it's very good. So your paper get published. That's why we chose ResNet, because it has the best performance. AlexNet. AlexNet do have a small computer, but it's still memory heavy, and its accuracy is too low. It's less than 55. It's almost random. It's like right or wrong. It's a random prediction. Sorry, no. But 55 is no. You can take like 10 minutes to write nowadays you can take 10 minutes use Berton to write a network out from AlexNet. That's why no one compared to AlexNet. The reviewer will say, why are you comparing to this thing? We all know it doesn't work. There's no way to waste your time. Yeah, the ResNet. Practical application. Yeah. This forward time per image is like how much time it takes to predict. Because when you predict, you only do the forward, you do not do the back propagation. Which one? Oh, not surprised. This one, PGG, takes the most time, right? The first one is of the AlexNet. Actually, it's just different format of this figure. Anyway, AlexNet is very fast, but so what? It gives wrong prediction. Here's the ResNet. Here's the ResNet. It's in the middle. So we have a very reliable prediction with a pretty fast forward processing speed. So that's why actually some top conference like Microsoft, like Apple, they use GoogleNet Phone, sorry, not the original GoogleNet. But some second layer companies, they use ResNet, because you know, in deep learning, the accuracy always be the number one important thing. So if they have the best accuracy, they can sell their products in an easier way. This one is power consuming. It's like how much power it costs, it costs to do the prediction. When should you care about these things? When you do a cell phone, when you do some software for cell phone, because cell phone rely on battery, and not every power, every macro power, or every power is very important for a cell phone, because you need to cooperate with different departments. Everyone, the cell phone only have like 4,000 or 5,000 battery. Everyone needs to use it. So if you take more, I do not have much power. I do not have enough power to do my job. So you have to make it tiny and tiny. That's the only condition you need to worry about. And maybe if you do supercomputer, you need to care about the power, because you have thousands of networks, thousands of GPUs. You need to care about power. Otherwise, if you do a research work or something, we do not care about how much power it takes. And if you publish a paper that I developed a new network and it's super efficient in energy, I guess you have 80% to get rejected because no one cares. There 20% is that your reviewer is someone working in the like mobile device area or supercomputer or something. Otherwise, we just care about, do you have their top conference? Oh, sorry, do you have their SOTA, state-of-the-art performance? Yeah. Then I'll give some very brief introduction to some new architectures. 2016. This one is not as famous as the ResNet one, coming published in 2016. It's an improved ResNet block, designed from creators of ResNet. Well, we say it used to be convert batch reload, convert batch reload. It changed, as you can see, it changed the order, right? That's the only difference. It creates a more direct path for propagating information throughout network. Sure. Because here is a convert layer, right? After convert layer, there's no reload, so there's no cutoff. So it just put it here. And in the previous version, it have after convert you have bn reload. So here this part, convert bn reload, and here you have a cutoff of the negative part. So you only put the positive part here. Sorry, what?
What is the BN?
Batch normalization.
Oh.
BN. Wider red view. So as you can see, after the REST block comes out, there's a lot of transformations of the original one. We make it wider, we make it deeper, we put something different inside, we put something different outside, and it's like Lego. This work argues that residues are the important fact, not the dips. It means the counter dips, not in this direction. These wider residue block F times K filters instead of F filters in each layer. 50 layers wider outcome. Yeah, they compare with the original ResNet. They said we only use 50 layers to have a better performance than your original 152. So this format is turned the ResNet into a parallelizable network. But to be honest, I never see anyone use this network or compare with this network. But this one do have some citations. The ResNet. It increases the width of residue block. Use different parallel pathways. So they are the same. Yeah. Same format.
Is that ResNet plus inception?
Sorry, what?
So on the previous graphs, you had like the best one was ResNet plus inception on the chart that was charting accuracy of the top left prediction.
I'm sorry.
So you look at the slide 35.
35.
You have inception before. Is that
Oh.
showing? Is that is like that's where you have it's like Google Net right
No.
now.
No. As I said here, GoodNet have different kernel size, if you remember it clearly, right? 1 by 1, 3 by 3, 5 by 3, 5, 7 by 7.
Right.
They are using the same kernel size. But I'm pretty sure they are inspired by GoodNet. But here's the difference. They have 32 classes. Much, much bigger than GoodNet. Because GoodNet have 1 by 1, 3 by 3, 5 by 5. Maybe 7 by 7. But you could not do 9 by 9 or maybe 11 by 11, right? It's too big. So that's the difference. And ResNet get popular for a very short time, like 2018, 2019 or something. But only the original things last for the longest time. Deep networks with shortest depths. Motivation reduce managed gradients and tension times. It's like using dropout. It randomly drops some subset. Like dropout, if you remember, dropout drops some kernels, some kernels in a layer. This one drops some blocks in the network. And of course, it uses all of the blocks for the test. This paper is the best in 2016 challenge. They use more simulation of inception ResNet and classification. fusion. Fusion. Fusion is a very fancy idea. It's like to focus. Like for an image, there's some part should contribute. Like if a dot in the middle of the image, then the middle part should your network focus on instead of the border part. That's the very common use for fusion, or we call focus. Fusion? No, it's fusion. We call focus fusion. Issue. What's the structure? So it put different structure together. We call fusion. Yeah. Never mind. This one, the SENet. That's why we have ResNet, non-name SENet, because no one knows him anymore. SENet. This is what I mentioned. What I said. We get a focus of different parts. This one, we used to give focus, give different weight on different parts of their feature, like this part or this part. But SENet give different weights on different channels. Like here's the channel, different color is different weight. Here's the original output, and they have a bypass to calculate one by one by C. C is their weight for different channels. And they use this different weights to weigh their prediction. So in this way, they give some focus on some specific channels, not instead of different parts. If we focus on some part, it will be the same way for all channels. So it's like a different dimension. They give a feature recalibration model, this model, like here. They have FC, global Boolean FC sigma to calculate their weight. Global information plus 2 FC layers used to determine feature map weights. It's I can say first published this thing in WCV or something, and after that they published it in CPR or WCV workshop. CPR. Yeah, this one. It's called DenseNet. Their dense block. Like this block, where each layer is connected to every other layers in feed-forward fusion. Like you see here, connect to this one, this block, this cover, and the last cover. So that's why I call dense. Active vanishing gradients, stress feature. Yeah. It's a key point for this structure is that it encourages the feature reuse, because we do a convert here, we got some feature, and if we simply pass it to the next layer, it only be used once, and this layer will use the output of this one. But we contact it here, this layer will use the features from this layer and this layer. So it encourages the feature reuse.
What do you mean forward action? Like, is that adding? What do you
it's using, as you say, using concat. So like, if I have a WHC, right? If the C is 10, if all of this output is 10. So here we have, we do not care about, like input. Okay. If we got a W by H by 10 tensor, right? Here. And after this convert, we got a W by H by 10, okay? And we have concat here. We concat this WH10 to this WH10. So we have WH20. And we have WH30, WH40. So it's concat, not add together. If we add them together, we'll get WHC, still WHC, right? Squeeze now.
And that's along the feature dimension is kind of
Along channel dimension. Actually, we have add and concat. In most conditions, you can use add, but DenseNet use concat. That's why it's called DenseNet. If you change it to add, it will also work, maybe with not that high accuracy, but it will still work. But it doesn't call DenseNet anymore.
Well, that's true, because that would be ResNet.
Oh yeah, ResNet use that. Yeah. But
Is it adding?
sorry.
So this is different from ResNet, that it doesn't do the normal adding process.
For this one, it do not need add, but sometimes this convert will become a residue block. So residue block, dense connection, residue block, dense connection. It's like Lego. You can put them together and in either ways, you know, and then you compare the performance. You take the best one and you see, oh, we developed a new structure. But actually, you test millions of possibilities and you find the right one. The squeeze net. Fire models consisting of a squeeze sphere. Yeah. This model, I guess, is specially designed for some mobile devices, cause like the mobile net, because it's almost 500 times smaller than AlexNet. It only have 0.5 megabits parameters, so it's very tiny. So this model is working on different dimensions. It's not like how to improve my prediction accuracy. It's like how to make my network smaller and smaller to make it running faster. On this one, there will go some different things like meta learning. It's like before this part, we are talking about different net structures. We manually design these net structures, including AlexNet and GoogleNet or VG ResNet. We design that network. We give a network and give their training data. Okay, their network just learning the parameter, right? The structure is fixed, but the meta learning is try to use try to learn the network structure. Controller network that learns to design a good network architecture. Other stream corresponding to network design. Either way, it not only like the ResNet VGG, it not only learns the parameters in a net structure, it learns which structure is good for this task. And after get this structure, you learn the parameters in this structure. So the previous net structures is a hyperparameter like manually designed. You saw it better, so you try it. But this one is learned. But it's not always good, I have to say. Iterate simple architecture from search space. Train the architecture to get a reward R corresponding to accuracy and compute gradients of simple probabilities. Actually, this part, this meta-learning, is a different topic in deep learning. The network structure we mentioned above, like from LandNet to ResNet, is how to use a network get a better performance. The meta-learning is how to train a deep learning model to get how to make the deep learning to design a deep learning model. It's a different topic. Learning to learn networks architectures. So like NASNet use NAS to find the best cell structure on small C5 engine. Usually these topics prefer to work on like C5 or MNIST dataset because it's really not that good on some very big dataset like ImageNet or MS Coco. So yeah, here's the summary. In architectures, we have introduced AlexNet, VGG, and Google NetNet and ResNet, and some transformation of 1, 2, 3, and 4 for different for different types, but based on ResNet and meta-learning. VGG, Google Net, and ResNet is all in wide use, available in Model Zoo, no matter you are using TensorFlow or PyTorch. ResNet is a very good default network, but you can try DenseNet and SENet. But I prefer to start it from ResNet because it will not make some very big mistake. We are using some very deep network nowadays, and significant research center around the final layers calculations, improve gradient flow. Yeah. Efforts to investigate necessary of dips and whys. Yeah. So here's the different the depth, the whys, and the residue of a network structure. There's different things you can change. Even more recent turn towards meta-learning. Yes, but it still got state-of-the-art performance in some common data set. The meta-learning still compared with other meta-learning structures, not like ResNet, DenseNet. No, they do not compare with us. They compare with other meta-learning structures. That's it. Any problem? No? Thank you.